These next few sections are extremely conceptual. So kind of taken from what it's worth, we have de Broglie, who talked about the dual nature of light and mass, and he really dealt with waves. We have Heisenberg, and this is not Heisenberg from Breaking Bad, and it really is about the limit you have in describing a position and a momentum. And finally, we have Schrodinger, and I've totally reworked my material for this online class in hopes of having you see the essence and get the insight that you need from this chapter. So we start with de Broglie, and there's an equation where wavelength is equal to Planck's constant divided by mass times velocity. We don't do too much with it. We just want to show it to you. And what you have here is wave, because it is wave nature of light. And here we have mass, which is a property that normally is not associated with a wave. So what he did is he said photons. We have our E is equal to h nu, or EC over lambda. And we also have Einstein's equation, E is equal to mc squared. So what I'm going to do is rewrite them using the substitution of velocity for speed of light. And as you can see, we can now cancel things out. We have h divided by wavelength is equal to m times velocity. And what we did is we solved for wavelength. And that is where the equation came from. Much, much more work than that, but not something that we have to deal with. So in order to kind of show you why it's important, I chose three things. I chose the Earth, I chose a bullet, and I chose an electron. If I put in values for typical masses, if I put in values for typical speeds, I can come up with the wavelength that is part of this hypothesis. Well, if you look at 10 to the minus 58 meters, that I'd say is unrealistic. So this is not going to apply to something like the Earth. If I look at a bullet, I see 10 to the minus 23 meters, I'd have to also say that is unrealistic. But when I look at the electron, that's 10 to the minus 10 meters. Well, now we're on the order of nanometers, and that's where this really took off. Wave properties were then demonstrated experimentally using beams of fast electrons and single crystals, and in this case it was nickel. Important enough for me to say this on the next slide. They found that the wavelength of an electron was approximately the wavelength of an X-ray, and we can actually detect X-rays. So they have the pattern here from passing it through a crystal, and when they passed an electron through, it gave a similar pattern. Now this was really, really big, because we're trying to understand things. That leads us to Heisenberg's uncertainty principle, also done in the 1920s, and I wrote the equation up above. Again, it doesn't do it justice in this class, but let's kind of put it into perspective. If I take a ball and roll it down the ramp, I'm going to know its position, its direction of motion, and I'm going to know its speed. Maybe you did it in your physics classes in high school. But the question by Heisenberg was, could we do this for an electron? So he came up with that equation above, and he called it the wave-particle duality of matter. And it said, how precisely can we know both the location and the momentum of an electron? Now, I hope by now you've realized there's uncertainty in all the measurements that we make, and there are also limits to the accuracy. And for the most part, we don't have consequences with ordinary size objects. But when we take it down to the electron, that's when we're going to have to deal with some things we never had to before. So what I did here is I took two objects. I took a bullet and I took an electron, and I took some numbers. And again, the numbers are not that important, but what I did is I looked at what is the change in position if we're looking at a bullet. And that change is 10 to the minus 36 meters. I don't mean to say it's meaningless. I think I should have probably used the word unrealistic. But now, if I focus in on an electron, and again, made some numbers, plug them and chug them, and what I get is 10 to the minus 9 meters. It is still a very, very small number, but let's look at the hydrogen atom, which has that one electron. It has a radius of 0.37 angstroms, a diameter of 0.74 angstroms, and when I look at the conversion of angstroms to meters, I come up with 10 to the minus 11 meters. Well, to be honest, the error using the Heisenberg uncertainty principle, it is greater than the diameter of the hydrogen atom. So that's proof that the Heisenberg uncertainty principle does exist. A short section. What can you expect? Please do the homework problems. I notice Alex didn't quite cover this, so hit the topics in your textbook. I'll pull up things that have appeared on past midterms and discuss them with you in the lecture Zoom.